طيب, Bismillah ar-Rahman ar-Rahim. My name is Amjad. I'm a second year medical student. Today I'm going to give you the iron metabolism. Here's my number and my email. If you have any questions, feel free to ask. And inshallah, I will make it easier for you. I know this is like not hard, but inshallah, I will make it easy. طيب, let's start. Bismillah. Those are the objectives. We will talk about the function of iron. Why do we need it? How can we absorb it? How our body regulate the iron? And please, in this lecture, focus on the hepcidin, because I saw a lot of questions in the final past questions about hepcidin. Type, just a recap here for the heme structure. So what is heme? Heme is part of hemoglobin. You know that hemoglobin is a part of the RBC, and so the hemoglobin is found in erythrocytes, the RBCs, where it's responsible for binding oxygen. Specifically, this iron in the heme structure, in the hemoglobin, this iron is the one that will attach oxygen and transfer it in our body. So we have RBC. Within the RBC, we have something called hemoglobin. Heme is part of hemoglobin, and the iron in that heme will transfer the oxygen or bind to the oxygen. Type. Just a couple of notes for this lecture. We have, I know, just know for these for now, because it will make it easier for you to understand the concepts. We have two forms of iron. We have the ferrous iron, which is Fe2+, and the ferric iron, which is Fe3+. Our body can only absorb Fe2+. So when we eat something that contains iron, most of the iron in the food is ferric iron. And our body can only absorb Fe2+, which is the ferrous. So in this case, our body should convert the ferric into ferrous so we can absorb it. And we have the storage forms of iron called the ferritin and the transferrin. They can only bind Fe3+. We will repeat those as we go through the lecture. Type. Now let's begin the introduction. Let's talk about the function of iron in our body. So for the functional form of iron, first of all, it's important in hemoglobin, basically to attach oxygen and transport it through the body. It is also found in myoglobin, myoglobin iron in muscles. So myoglobin in the muscles, it stores the oxygen for muscle contraction. Also, iron plays an essential role in the enzymes, peroxidase, catalase, cytochromes, especially cytochromes here. If you remember cytochromes in the oxidative phosphorylation, where those enzymes transfer the electrons. So the iron here plays or act as a cofactor for those enzymes. So the cytochromes require iron to function. Okay, so the oxygen for the oxidative phosphorylation is carried by iron. And what else? Okay, for the storage form of iron. Now, how is our iron stored in our body? In two forms. First of all, ferritin. Ferritin is the storage form of iron in the cells. So inside cells, the iron is stored in the form of ferritin, and it is transported in the plasma through transferrin. Okay, so those are important. So ferritin stores iron inside, and transferrin will transport the iron in the plasma. Most of the iron in our body is stored either in the macrophages or in the hepatocytes. Small amounts are, all the cells in our body contains iron, but mostly macrophages and hepatocytes. Now there's something called hepcidin, which is basically a partially digested ferritin. So when the iron is stored inside the cells, there would be a time in which we need that iron to be released. And so the lysosomes, okay, will come and start to digest that ferritin, slowly releasing iron from the cells to the plasma because we need it. And so that partially digested ferritin is called hepcidin. Okay, now for the iron can be harmful in some ways, in which when iron can react with hydrogen peroxide, it will produce a free radical, hydroxyl radical. This is a harmful molecule in which it damages proteins, lipids, and the nucleic acids. So, so this is called the Fenton reaction. Keep this in the back of your mind. طيب. Now, how can we assess the iron in the patient? How can we know if someone has an excess iron or he has an iron deficiency? So we can look at multiple things. We can look at the serum iron, we can look at ferritin, transferrin, or transferrin saturation. However, the most sensitive one to look at is the ferritin. Now, the serum iron, if we measure the serum iron, it does not really help us to check the amount of iron someone has, right? Because why? What's the problem with serum iron? It does not tell us the amount of iron in macrophages or in the hepatocytes, right? We said that most of our iron is stored in macrophage and hepatocytes. However, if you measure the serum iron, this will not tell you the amount of iron stored in the cells. So that's why serum iron does not tell you if someone has excess iron or has an iron deficiency. However, the most sensitive marker is ferritin. Now, ferritin, we said it's an intracellular storage of iron, right? However, it can be present in the blood. So we can measure ferritin, and it will tell us the balance of iron in the cells and the iron in the blood. So basically, the ferritin, just know that it is the most sensitive marker for measuring the iron in the patient. And so ferritin is the intracellular iron storage molecule. It directly correlates to total body iron stores. This is the ranges, and this is the most sensitive marker for in diagnosing iron deficiency anemia. Then the transferrin, we said transferrin, also called the IBC. It's the protein that transport iron in the plasma. Transferrin saturation, basically, it's how much iron is bound to that transferrin. And now this is important. The iron deficiency, it will cause decreased serum iron, increased transferrin, and reduced ferritin. Now, okay, so iron deficiency, when someone has low iron, obviously the serum iron will be low. However, the transferrin will be high and the ferritin will be low. Now, why is the ferritin low? Because if someone doesn't have iron, he will not require ferritin to store it, because there is no iron in the first place, so ferritin will not be there. However, the transferrin will increase. We said that transferrin transport the iron in the plasma, right? So how our body responds is that the cells will start to synthesize more transferrin, so we can bring more iron. So that's how our body responds. So when someone has low iron, the serum iron will decrease. Okay, transferrin will increase. Okay, so that we can get more iron, and the ferritin will reduce or will decrease because we don't have iron. So we can look at those measurements together to check if someone has an iron deficiency or he's normal. Yes, iron is stored as ferritin mostly in the cells. Yes. Yeah, we said the ferritin is the storage form of iron inside cells. So all the iron inside the cells will be stored as ferritin, and mostly in the macrophages and the hepatocytes. Okay, the difference between transferrin and serum iron. So the iron within the plasma or the circulation, it is transported by transferrin. So serum iron cannot be alone. Okay, so it needs like a carrier to transport it. So it is transported through transferrin. Does that answer your question or not? Okay, so if you have any other questions, we will have a checkpoint in which I will answer all your questions. Okay, so now let's move on. Type. Okay, now focus with me here, please. Now let's talk about the body iron cycling. Now let's say you ate an iron, you ate a food that contains iron, okay? Now the iron will go to your intestine, and here's the enterocyte, تمام? And then this iron will be absorbed through the enterocyte, and then it will go to the plasma. It will bind to attach to transferrin, and then the transferrin will transport that iron to the bone marrow. So this is the bone marrow in which there is erythropoiesis, or the production of RBCs. So the iron will go there because we need iron for erythropoiesis, and then this is the full mature normal biconcave RBC with the iron, with the hemoglobin, or everything normal. Then after 3 months, 120 days later, what will happen? This should be destroyed. So, and it will go to the spleen, in the macrophage. This is a macrophage in which the RBC will be destroyed. This is called the senescent RBC. So RBCs after 120 days, they should be destroyed, and we form new cells. So when the RBC go to the macrophage, what will happen? It will be destroyed, releasing this iron. Okay, it will be destroyed by the enzymes within the macrophage, therefore releasing this iron. Now this iron will be either stored in the macrophage or the hepatocyte, or it will be released. Now it depends on the amount of iron, or the amount of iron that the bone marrow requires. If we need iron, it will be released. If we don't need iron, it will be stored in the macrophage. So if this iron is needed, it will be released from the macrophage in the form of transferrin. Then it will go to the hepatocyte if stored here, or if needed in the bone marrow, it will be released also by through transferrin, and then go to the bone marrow because we require iron for the erythropoiesis. Okay, here's for the regulation of iron, there is an important protein which is called hepcidin. So hepcidin is a regulatory protein formed by the liver, by the hepatocytes. They produce a protein called hepcidin. Now this hepcidin is important for the regulation of iron. Why? What is the role of hepcidin? Hepcidin basically, what is released by the hepatocyte, it will go to the macrophage, it will inhibit the release of iron, and also it will go to the enterocyte to decrease the absorption of iron from the enterocytes. So when we have, so basically hepcidin, it senses the amount of iron in our body, and accordingly it will, if we have excess iron, it will go and inhibit the release of iron from the macrophage, or the iron absorption from the enterocytes. So this is basically the function of the hepcidin. Okay, everyone got this? Senescent RBCs means the old RBCs that are that should die in order to make new RBCs. It basically means old RBCs. There's a question about how serum iron increase and transferrin decrease. You mean for this one? You mean this one, decrease serum iron and increase transferrin? I will get back to you for this question, Tamam. I will go back later for it, Tamam. Osama, I think. طيب. طيب, now let's talk about this one, about this part, the enterocyte and how our body absorb iron. طيب. So let's start. I want you to focus with me here on the right, on this image. Just let me find the pointer. طيب. Now, let's say you ate a meal that contains iron. Now, first of all, I want you to know that most of the food contains the ferric iron, and our body can only absorb ferrous iron. So we need something. So this is the GI here. This is the lumen. Here's the enterocytes. Okay, and here's the interstitial, the interstitium and the plasma. Type. So let's say you ate a meal that contains iron. Now we need something to convert this ferric iron to ferrous iron. So we have something here on the plasma membrane. It's called the duodenal cytochrome B. So the function of duodenal cytochrome B is to convert ferric iron to ferrous iron. Why? Because our body can only absorb ferrous iron. And then this ferrous iron will be absorbed through a transporter called DMT1. It's called the divalent metal transporter right here, DMT1. Now this ferrous iron is absorbed. Here it is. Right. There's another form of iron found in the meat. So if you eat meat, you'll have an iron in the form of heme. And actually, this is a better source of iron in terms of being used and absorbed. So this heme our body can also absorb this heme by heme transporter. So here's heme will enter the enterocyte. But however, we need to extract this iron, the ferrous iron from the heme. This is done by the enzyme called the HO1. Where is it? The heme oxygenase. Okay, this heme oxygenase will extract this ferrous iron from the heme. So now we have the ferrous iron, Fe2 plus right here. Then what will happen with this ferrous iron? It's either going to be stored in the enterocyte in the form of ferritin, okay, by the enzyme ferroxidase. It's somewhere here. Yes, this is ferroxidase. So it will convert this Fe2 plus into Fe3 plus in order to be stored as ferritin. Why should we convert Fe2 plus to Fe3 plus? Because ferritin, we said it can only bind Fe3 plus. So in order to store it, we need to convert it by the ferroxidase enzyme. Therefore, now we have the Fe2 plus stored inside the cell in the form of ferritin. When does that happen? When the body does not require iron, we have excess iron, so we store iron in the form of ferritin. Or in the second case, when the body requires iron, it will go and then it will be released from the enterocyte by a transporter called the ferroportin. So now ferroportin will take this Fe2 plus and then release it from the enterocyte. Now, when we release that Fe2 plus, we need something also to convert it to Fe3 plus. Why should we convert it again? Because the transferrin, which is the protein that transport iron in the plasma, can only bind Fe3 plus. So we have another protein called the hepcidin on the plasma membrane also. It will convert Fe2 plus into Fe3 plus. Why? Because Fe3 plus, or the transferrin, this one here, can only bind Fe3 plus. So now iron is bound to the transferrin, and now it can go to wherever, the bone marrow for erythropoiesis. So that's for the iron absorption. Now everything I said is like written here in text. So let's go through it. First of all, iron can be absorbed in the intestines as heme, this one, from the animal food source like meat, or as Fe2 plus. The heme iron is released from protoporphyrin by heme oxygenase. Okay, this one, heme oxygenase enzyme. Most of the iron in our food is Fe3 plus, so we must convert it to Fe2 plus by duodenal cytochrome B. This one here, duodenal cytochrome B. It will convert ferric to ferrous iron, and then the ferrous iron can be transported to the enterocyte by the DMT1. Now the levels of those two, these duodenal cytochrome B and the DMT1, increase during hypoxia by the HIF2 alpha. Basically, HIF2 alpha is transcription factor that it will increase the synthesis of these those two during hypoxia. Hypoxia means low oxygen, and obviously during hypoxia we require more iron, right? So we can have more RBCs and more iron. So we can have more RBCs or more, so that oxygen can bind to iron. Okay, so just know that during hypoxia, we have the HIF2 alpha that will upregulate the transcription of DMT1 and D-cytochrome B. And the iron inside the cell will be stored as ferritin, which has a we said the Fe2 plus will be stored as ferritin by peroxidase activity. Type. Now, and we said that also the ferroportin, this one, the transporter for iron, will transport iron from the enterocyte to the plasma. And okay, when there is available iron, okay, when we have iron is available, the hepatocyte, we said it will produce a protein, important protein called hepcidin. So the role of this hepcidin is to inhibit this ferroportin. So when this is inhibited, the iron cannot go to the plasma. Okay, so when hepcidin is released, when we have a lot of iron. So when the liver produces it, it will inhibit the ferroportin. Therefore, the ferrous iron cannot be released. We talk about the hepcidin, which converts Fe2 plus to Fe3 plus, and apotransferrin is basically this is apotransferrin. Basically, it's transferrin without iron. When iron binds to transferrin, it becomes transferrin or holotransferrin. And that's it for the absorption of iron through the enterocytes. Type questions about this part. Repeat the function of hepcidin. Okay, I will, because this is really important. You have to know it. And yes, the iron stored in the hepatocytes and the macrophages. Yeah, it's the form of ferritin. Anything related to iron inside cells is ferritin. Right, let's go about the for the function of hepcidin. So here, you see this hepatocyte. It produces a protein called hepcidin. Now, what is the role of hepcidin? 1 minute, please. Okay. So when the iron concentrations in our body is high, the hepatocyte, the liver cells, will produce hepcidin. Now, this hepcidin will sense or will measure the amount of iron in our body, and it will so when we have basically, let me rephrase it, please. Right. When we have a lot of iron, what happens? Hepcidin will be released. The function of hepcidin is to go to the macrophage and inhibit the release of iron. So this iron will not be released. It will stay in the macrophage in the form of ferritin. Or it will go to the enterocyte and decrease the absorption of iron. So this iron will not go to the plasma. It will stay here in the enterocyte, also in the form of ferritin, right here. You see this? The ferritin in the enterocyte. So basically, this is the role of hepcidin. Also, look here, the liver hepcidin. So how does hepcidin decrease the absorption of enterocyte and decrease the release of iron? Sorry, reduce the absorption of iron from the enterocyte and decrease the release of iron from macrophage by degrading the ferroportin. So when the hepcidin degrade this one, ferritin cannot be released, right? So this is how hepcidin work. Exactly, it regulates the amount of iron. So when we have a lot of iron, the bone marrow does not require iron. The hepcidin will be released, and therefore it will do two things. Okay, it will decrease the absorption from the enterocyte, and it will decrease the release of iron from macrophages. Hepcidin inhibits ferroportin. Yes, hepcidin inhibits ferroportin, but it does not inhibit the duodenal cytochrome B and the DMT1. They still can be absorbed, but they will not go to the circulation. They will stay in the enterocyte here in the form of ferritin. Now let's move on. Here's some factors that influence the absorption of iron and some factors that reduce the absorption of iron. Here we said the factors favoring the absorption of iron, like heme, ferrous iron. We said that our body can only absorb ferrous iron. Acids like vitamin C or orange juice can increase the absorption of iron. Agents like sugars and amino acids reduce serum hepcidin, will increase the absorption of iron, as we said. And ineffective erythropoiesis, pregnancy, hemochromatosis, we'll talk about this at the end. Factors that reduce the absorption, ferric iron, alkalis, antacids, agents like phytates, phosphates, increase serum hepcidin, will decrease the absorption of iron. This is important. This column is important, or row, because when the serum, we said that if the hepcidin is increased, it will decrease the absorption from the enterocytes by degrading ferroportin. Also, decreased erythropoiesis will reduce the absorption of iron. And inflammation, because inflammation produce interleukin-6, which will increase hepcidin. We will talk about this at the end also. Type. Now, I want you to focus with me here also. Type. Now, regulation of body iron by hepcidin. Now, let's say, so I will start from here. Do you see this? The holotransferrin. Now, holotransferrin, we said, no, the iron is bound to transferrin. Now, this is holotransferrin, which is basically transferrin bound to iron in the plasma. Now, this is a hepatocyte. This is a cell in the liver, hepatocyte. Now, when we have a holotransferrin, it will go to the hepatocyte. It will bind to TFR1, which is the transferrin receptor 1 and 2. Now, when it binds to those receptors, it will activate this complex. Now, when this complex is activated, the SMAD will be phosphorylated. When this SMAD is phosphorylated, it will go to the nucleus and enhance the transcription factor of hepcidin. So now we can have increased hepcidin mRNA and therefore increased hepcidin production. And this is how hepcidin is produced. And okay, so now this is how hepcidin is produced in the liver cells, in the hepatocytes type. There should be a balance also, right? So we need something that inhibit the release of hepcidin or the production of hepcidin. This is called the matriptase. This matriptase will come and inhibit this complex. So when you inhibit this complex, the SMAD will not be phosphorylated, so it will not go and enhance the transcription factor for hepcidin. Therefore, the hepcidin will go down. Okay, so this is how hepcidin is regulated within the hepatocytes. So when we have a lot of iron here, when we have holotransferrin, which is transferrin bind to iron, we all this process will occur in order to increase hepcidin. Or when the when we don't have a lot of iron, the matriptase will come in order to decrease the production of hepcidin. So basically, we have a balance between holotransferrin and matriptase. The more the holotransferrin, the less the matriptase, and vice versa. So everything is also written in the text. When body iron is full and the transferrin is saturated, here you go, here the holotransferrin. The diferric transferrin binds to the receptors TFR1 and R1 and R2 on the hepatocytes. They will activate this complex. Don't worry about the names. Just understand the concept. So when this complex is activated, So when this complex is activated, it will phosphorylate SMAD. When SMAD is phosphorylated, it will go to the nucleus and then increase the hepcidin production. Number 3 here, matriptase 2, it will go and inactivate this complex, and the opposite will occur. Again, hepcidin is carried in the blood to enterocytes and macrophages, and it will bind to the ferroportin and prevent the ferroportin from releasing iron. Or when the iron is low, the hepcidin will decline, right? Because when we have low iron, hepcidin should decline so we can release iron from the macrophage and absorb more iron from the enterocyte. So when the hepcidin declines, the ferroportin, which is the transporter in the enterocyte, now is more active, and then iron can enter the blood from the enterocyte. Also now iron can be released from the macrophages and the hepatocytes. Hepcidin reduces the iron absorption and release from macrophage by stimulating the degradation of ferroportin. We talked about this. So is this regulation step understood? The matriptase, this protein matriptase, it will inhibit this complex, and therefore you cannot phosphorylate SMAD. SMAD in this case is basically an enhancer of transcription. In order to perform its function, it should be phosphorylated. So in this case, if matriptase came, it will inhibit this complex. So SMAD cannot be phosphorylated, and therefore it will not enhance transcription of hepcidin. Therefore, less hepcidin produced. Make sense? تمام. طيب, let's move on. Again, iron regulation by erythroferrone. طيب. We have something called erythroferrone. Erythroferrone basically is produced by erythroblast. I think you know erythroblast more than me. It's like a precursor of red blood cell. It will produce erythroferrone. This erythroferrone will control the hepcidin release. Now, before going to the text, focus with me here on the right. So here's hepcidin synthesis. We said that the role of hepcidin is to go to the macrophage and inhibit ferroportin. Okay, do you see this transporter, ferroportin? It will go and inhibit it. So it will inhibit the iron release from the macrophage. It also go to the enterocyte and inhibit or decrease the absorption of iron from the GI by also inhibiting ferroportin. Normally we have iron absorption here and iron release. They will go and be transported by transferrin. Now this transferrin saturation the transferrin basically will transport this iron to the bone marrow for erythropoiesis, which is the production of RBCs. Now, when we have a lot of transferrin saturation, we have a lot of transferrin that is saturated by iron, like here, plasma transferrin saturation, it will enhance the synthesis of hepcidin. So remember, two things that will enhance the hepcidin synthesis: the plasma transferrin saturation. Here, the meaning that basically that iron is bound to transferrin. So when we have that transferrin saturation, it will increase the hepcidin synthesis, and therefore it will decrease the iron from here and here. Another thing is inflammation. It produces an inflammatory cytokine called the interleukin 6. This interleukin 6 also activate the hepcidin synthesis. Things that inhibit hepcidin synthesis is like erythroblast. How does it inhibit hepcidin? By producing erythroferrone. Also hypoxia, because we said we need oxygen, so we need more iron in order for oxygen to bind. Erythropoietin, which is the hormone for erythropoiesis, it will inhibit the hepcidin because we require more iron. And matriptase, as we talked in the previous slide. So for the erythroferrone story, basically, the erythroblast, where is it? The erythroblast, it will produce erythroferrone. This erythroferrone is a protein that controls the hepcidin release. It will inhibit the hepcidin release. Okay. So the gene for erythroferrone is controlled by erythropoietin, the hormone erythropoietin. In anemia, elevated erythropoietin will stimulate erythroblast to secrete ARFE. So during anemia, when we have low RBCs, what will happen? The erythropoietin will increase. Okay, so the hormone for the what is it called? The production of RBCs. Okay, so this erythropoietin will stimulate the erythroblast because we need more RBCs, right? We have anemia, so we need more RBCs. So the erythropoietin will stimulate erythroblast. This erythroblast will secrete erythroferrone. Now the erythroferrone will decrease the liver hepcidin production because we require more iron. So this explains the excess absorption of iron in anemia, where ineffective erythropoiesis increases the erythroblast and erythroferrone. And the hepcidin synthesis is increased by transferrin saturation and inflammation. We said the transferrin saturation and inflammation will increase the production of synthesis, synthesis of hepcidin, and it will be reduced by increased erythropoiesis, erythropoietin hypoxia. Deficiency in hepcidin production can result in iron overload. Okay, so when you have a very low hepcidin, this may develop an iron overload in which you have an excess or accumulation of iron, like in this case, hemochromatosis. We will talk about it at the end. So is this clear? The regulation of hepcidin and the role of erythroferrone. Sorry. Now we have iron. We need to know the mechanism or the process in which iron can enter the cells. Now we said that iron can be present in all our cells, right? So how does this iron go from the plasma inside our cells? So let's take an example. Let's say this is a muscle cell, okay? And the muscle cell obviously requires iron. Why? Because iron, we said, it has an important role in the cytochromes, which is required for the ATP production. Now we want to know how does this iron enter our cells. So start from here by the apotransferrin. Apotransferrin basically is, we said that transferrin is the protein that transport iron in the plasma, right? So we have apotransferrin and we have iron. So when iron binds to the apotransferrin, it becomes the transferrin or the holotransferrin. Okay, so basically the apotransferrin is transferrin without iron. When iron binds to the apotransferrin, it becomes the holotransferrin. Right. Then the next step, it will bind to the receptor here, the transferrin receptor, and then it will mediate what's it called, the receptor mediated endocytosis. So this iron, this holotransferrin will bind to the receptor. Now we have an endocytosis in which this will pinch off from the plasma membrane. It will enter the cell, forming an endosome. Okay, what's the next step? Next step is that you have hydrogen, okay, H+. It will go to the endosome, and then it will separate the iron from the transferrin, right here. So the hydrogen is pumped into the endosome. It will separate the iron from the transferrin, and now the iron will be released from the endosome through DMT1. This is the divalent, what is it called? The DMT1, which is the transporter for iron. It's also present here. So now iron can go to the cytoplasm, and then the endosome will go back to the plasma membrane, and the cycle is repeated. So this is all the things I mentioned are written here in text. The holotransferrin here binds to the TFR1. Then it will be transferred to the cell through the endosome. Then the iron will move from the endosome to the cytoplasm by iron. Here again, the transferrin receptor has high affinity for the diferric transferrin. Here, right here, when the receptor 1 molecule bind transferrin, they will cluster together, and then this endosome will pinch off from the plasma membrane. It will go to the cell and form an endosome, and then the hydrogen ions will be pumped into the endosome. So the transferrin will release this iron, and then the iron will move to the cytoplasm through the DMT1. Okay, I will repeat, don't worry. Transferrin receptor is it's the receptor that binds transferrin. We said that transferrin transports iron in the plasma, right? So this transferrin here, this transferrin will go and bind to its receptor on the muscle cell, for example, or any other cell. And then this receptor with the iron will go to the cell. Inside the cell, now this DMT would release iron from the endosome to the cytoplasm. So let's repeat this again. Now we need to know how does iron enter our cells, because we said that we need iron for many things, like one function of iron is that the cytochromes in the cell, in the mitochondria, requires iron as a cofactor. Okay, so those enzymes require iron. How can we get this iron from the plasma into the cell? Now start from here, apotransferrin. Now apotransferrin basically is transferrin without iron. Don't worry about it. Now I want you from here, go from here. We have transferrin, okay, in the plasma. Normally iron is bound to it. Okay, now this transferrin will bind to its receptor on the cell membrane, this one, the transferrin receptor. Now when it binds to this receptor, what will happen? You have something called the receptor mediated endocytosis, in which this endosome will pinch off from the plasma membrane going into the cell. So now we have, what do you have inside the cell? Two things, the receptor and the iron, right? So now this endosome, the hydrogens will be pumped into the endosome. Now the iron will be separated from the transferrin. So now iron is released from transferrin, and therefore iron now can be released by DMT1 into the cytoplasm. Now we have the iron in the cytoplasm. Now iron can perform its functions, whatever function one function is, the cofactor for cytochrome enzymes, for example. Is it clear? Ferroportin, it releases iron from the enterocytes, into the plasma. Right. Everything here, I think I stated it. So let's just go through it. Cellular iron storage, the role of ferritin. We said that cells can store iron in the form of ferritin. Also, mostly in the macrophages and the hepatocytes, they contain the most iron storage. Ferric iron, which is Fe3+, is stored in a protein called the apoferritin, which then becomes ferritin. We said that apoferritin is basically without iron. When iron binds to it, it becomes ferritin or holoferritin. Ferritin can only be mobilized by the lysosomal degradation of the protein. So we said that the storage of iron inside cells, when the body needs it, the ferritin will be degraded by lysosomal degradation. And when this is degraded, the iron will be released from it slowly. And then something called hemosiderin will be formed, which is basically partially degraded ferritin. Now, to regulate the iron inside the cell and avoid free radicals, so we need to regulate the number of the transferrin receptor by regulating the transcription function of the mRNA. I will talk about this in the next slide. The result is that when the intracellular iron are sufficient, the production of the transferrin receptor declines. I will talk about this also in the next step, in the next slide. Okay. Right. Now this one is important also. We will talk about the regulation of transferrin receptor, which is this one here. the DMT1, and the ferritin by the iron response protein. Guys, do you want like a break to go and pray, or should we move on? Okay, Tom, let's take a break so we can go pray and come back. Tamam? Right, let's move on. Now we talked about the how does iron enter into our cells by transferrin receptor and the DMT1. Keep those in mind, the transferrin receptor and the DMT1. Now we will talk about how is this regulated. So we have something called the IRP. So focus with me here. So just to orient you, this is the IRP, iron regulatory protein. This is the mRNA strand for ferritin and ALA, and this is the mRNA strand for transferrin receptor and DMT1. Okay. Now the IRP, the iron regulatory protein, present in two states. Sorry, I will. Okay. So for the IRP, it occurs or present in two states: a low iron state and a high iron state. When it's in the high iron state, it will not bind to the IRE. What is IRE? It's the iron response element type. Now, leave this for now. I want you to focus on the low iron state. So when the IRP is on the low iron state, it will go to the 5' end of this mRNA strand. It will bind here to the iron response element, and it will inhibit the translation. It will block the translation of ferritin and ALA synthase. ALA synthase is an enzyme in the heme synthesis process. So when we have a low iron state, it will come here, bind to the IRE on the 5' end, therefore block the translation of ferritin and ALA synthase. It makes sense, right? Because we said that when we have a low iron, we don't need ferritin, right? Because we said ferritin stores iron inside the cell. So if we don't have iron, we don't require ferritin, and the same for ALA. Another thing the IRP does is it will go to the 3' end of this mRNA strand, and it will stabilize this mRNA strand, and therefore increase the protein synthesis or increase the synthesis of transferrin receptor and DMT1, which also makes sense because when you have low iron, you need transferrin receptor 1 and you need DMT1. Why? Because as we said, we need this, right? We need transferrin receptor 1 and DMT in order to have more iron inside the cell. So basically, this IRP, it will sense the iron inside the cell. When it is low, it will go and bind to the 3' end of this mRNA strand, and therefore increase the synthesis of transferrin receptor and DMT1, so we can have more iron inside the cell. Does it make sense? And everything is stated here in text. So when the IRP binds to the iron response element within the 5' end, it will inhibit the translation of ALA and ferritin. And when it binds to the 3' end on this mRNA strand, it will increase here. When the IRP binds to the IRE in the 3' UTR, it will bind to the TFR1 and the DMT1. So this will stabilize this mRNA strand. So there will be an increased protein synthesis of those two, the transferrin receptor and the DMT1. Okay, I will repeat. So let's go from here. So I'm talking about here, it's all related to this one. I want you to keep transferrin receptor in your mind and also the DMT1. And this is a cell, okay? Let's say a muscle cell or whatever cell. So we have two things, transferrin receptor, DMT. What happens? We have something called IRP, iron regulatory protein. Now this IRP will sense the amount of iron intracellularly. So see here, intracellular iron is sensed by the IRP. Now, when there is a low iron state, so iron is low inside the cell, what happens? The IRP will go and bind to the 5' end on this mRNA strand. When it binds to this 5' end, it will block the translation of ferritin and ALA, which makes sense because when we have a low iron inside the cell, we do not require ferritin, right? Because we said ferritin stores iron inside the cell. If we don't have iron, we do not require ferritin, and also for the ALA synthase. Second thing it does, the IRP, it will go to the 3' end of this mRNA strand, and it will stabilize it. In other words, it will increase the protein synthesis of transferrin 1 and DMT1. So in this case, we have low iron, right? This is the low iron state of IRP, this one. It will go and bind here to this mRNA strand at the 3' end. Therefore, it will stabilize it. It will increase the production of transferrin receptor 1 and DMT1 so that it can bring more iron to the cell. No, during high iron state, look, when the IRP is in the high iron state, it will not bind here. See here, like IRP exists in 2 states. At high iron, the IRP binding iron, it will reduce its affinity for IRE. So when it's in the high iron state, it will not bind here. So we can have ferritin and ALA. Is it clear? 221455. Okay, تمام. طيب, let's move on. So everything I explained is here written in text, so just give it a read. And checkpoint. Does anyone have any questions so far? Or should I move on? Right. Iron recycling. I think everything stated here is I said, but let's go through it. The largest percentage, most of the iron we get from is from the recycling of RBC, not from the diet. Okay, we said that the senescent or the old or the aging RBCs will go to the macrophage in the spleen. They will be digested, and therefore the iron is released from it, and it will be stored as ferritin. However, if our body needs this iron, it will be released. It depends on the hepcidin. Also, the iron is stored in the hepatocytes and macrophages. They have the ferroportin. So if our body needs the iron stored here and here will be released. We have something called haptoglobin and hemopixin. Basically, those are plasma proteins that what was the function of those? They will bind to the hemoglobin and heme. Okay, the haptoglobin will bind to the hemoglobin, and the hemopixin will bind to the heme. So they are not excreted through the kidney in the urine, because we said that we require those hemoglobin and heme for iron recycling. We don't want to lose this heme and hemoglobin. Okay, so when those proteins, plasma proteins, haptoglobin binds to the hemoglobin, hemopixin to heme, they will not be filtered in the glomerulus, in other words, in the kidney. So they are not filtered out in the urine. So the heme and the hemoglobin will be retained in the body. Why? Because we need that iron. Okay, and what else? The macrophage carrier receptor for, okay, that's not important. Type. So basically, the haptoglobin and the hemopixin are plasma proteins that bind to heme and hemoglobin. So they are not excreted in the urine because we need those for iron recycling. Everything here is, as I said also at the beginning of the lecture, so just give it a read. They are easy, they are understandable, self-explanatory. Then here, iron overload. What happens when someone has an excess iron, or in other words, iron overload? Okay, from here, we have iron overload may occur in a disease called hereditary hemochromatosis. I put the definition of this disease here. It's basically a disorder in which the body built up so much iron. So basically, iron overload can occur in hemochromatosis or secondary to chronic anemia and their treatments. Iron overload is harmful to us. Why? Because now iron can react with hydrogen peroxide, really producing the Fenton reaction. Now this the ROS, the reactive oxygen species, or the free radicals, they are harmful because they destroy lipids, proteins, and nucleic acids. They will cause cell damage and death to the liver, heart, and pancreas. Yes, this is important. We have chronic anemia called hereditary hemolytic anemia. Now, hemolysis means destruction of RBCs. Anemia means low RBC. So this condition is called hereditary hemolytic anemia. It will cause iron loading. As in beta thalassemia, you have the hemolytic anemia. This will cause iron loading. Now, let's know why. Why does it cause iron loading? Because when you have a lot of destruction of RBCs, like abnormal destruction of RBCs, the bone marrow will be overactivated, so it can make more RBCs, right? So what will happen? It will develop erythroid hyperplasia. Hyperplasia means increased number of cells. Okay, so basically the bone marrow will be overactivated. So what will happen? More precursors of RBCs will be produced. Example is erythroblast. Now we said this erythroblast in a previous slide that it will increase something called erythroferrone. Now this erythroferrone will decrease hepcidin, and you know what happens if hepcidin is decreased? The iron will be released from the macrophage, and it will be there will be a lot of absorption of iron from the enterocytes. What is the outcome of this? Iron overload, right? So this will result in increased iron absorption and recycling. So this is how chronic hemolytic anemia will cause excessive accumulation of iron. Do you get this hemolytic anemia? Why does it cause iron overload or the accumulation of iron? Okay, but now this is important also. Remember this disease because there is a question in the final for it. Anemia of chronic inflammation. Now, we said in the previous slide also that inflammation produce a molecule or the inflammatory mediator or a cytokine called interleukin-6. So let's say you have a chronic infection. Chronic infection can lead to inflammation, malignancy, the cancer, autoimmune diseases will cause inflammation. This will produce or will activate the leukocytes and the macrophages to release interleukin-6. Now this interleukin-6 will act on the liver to increase hepcidin. Now what happens when you have increased hepcidin? It will go to the intestinal enterocyte. What will it do? It will increase the iron absorption, and it will go to the macrophage and hepatocyte and decrease the iron release. So what you'll have because of this, you'll have anemia, right? That's why it's called anemia of chronic inflammation. So because of chronic inflammation, a lot of interleukin-6 will be produced. So this will increase the hepcidin. Hepcidin will decrease the iron absorption and the iron release, causing anemia. So anemia is a systemic disease. It is caused by inflammation, can be caused by inflammation. Examples, rheumatoid arthritis, okay, and other infections like AIDS and HIV. Know this rheumatoid arthritis. Know that RA is a inflammatory condition that releases interleukin-6. So what will happen? Hepcidin is an acute phase protein, yes, we know. In inflammation, the liver will increase the hepcidin release in response to the interleukin-6, this step here. This will increase regardless of the systemic iron levels in the body. It means that the hepcidin will not like act due to the how much iron we have in the body. No matter what, no matter how much we have iron, the interleukin-6 will activate hepcidin, and hepcidin will decrease the iron absorption. So what is the effect of this? The effect of hepcidin in this case, it will decrease iron absorption, it will increase the iron release. Although there is plenty of iron in the body, it is unavailable to developing RBCs. Why? Because in this case, it is trapped inside the cells. So this iron cannot go to the bone marrow, and therefore we cannot do more RBCs, right? So because they are trapped in the enterocytes and the macrophages and the hepatocytes. So for this slide, it's important. In a summary, you have a chronic infection, you have a malignancy, autoimmune, mainly chronic infection. this will produce or activate the macrophages and the leukocytes to produce inflammatory mediators, interleukin-6, which stimulate the liver to produce hepcidin, and then you know what will happen, and also produce those leukocytes, produce TNF-alpha, interferon gamma, interleukin-1, will also decrease erythropoiesis and decrease erythropoietin, which is the hormone required for erythropoiesis, therefore causing anemia. Does everyone got this slide? Understand it? So if you have any question regarding this slide, please write it down. Let's move on. Now this is the same thing. We have something called lactoferrin. Now lactoferrin basically is a protein. It's like a protein in which iron combined to. However, this is in the neutrophils. So we said elevation of hepcidin during inflammation is a defense against invading bacteria. Yeah. So why does our body increase hepcidin in this case? So we can reduce iron absorption and iron release, right? But why? What's the reason? So because, for example, bacteria has like it uses iron for its metabolic processes. So if we inhibit that iron, bacteria will not like it will die. Okay, so if you keep this iron inside the cell, it will reduce the iron available to bacteria, and this will contribute to their death. So that's why our body react like this. Okay, that's why it increases hepcidin, so it can deplete that iron from bacteria. So now this contributes to the death of that pathogen or bacteria. Now we have a lactoferrin. As I said, lactoferrin is an iron binding protein. It is present in neutrophils. Okay, this lactoferrin is important. Why? Because it will prevent the phagocytose bacteria. Now when we have an invasion by bacteria, it will be phagocytosed by the neutrophils. Now inside those neutrophils we have lactoferrin. So this lactoferrin will bind to iron and prevent that bacteria from getting this iron. Okay, so this is how lactoferrin works. So it can deplete iron from bacteria, so it can die. It may also provide protection for the phagocyte from oxidized iron. Now normally the neutrophils produce ROS, the reactive oxygen species, in order to kill the bacteria. However, when there is no bacteria, this lactoferrin in the neutrophils, okay, this lactoferrin in the neutrophils will bind that iron so that the iron cannot undergo the Fenton reaction, because so it does not produce the ROS. Because if there is no pathogen or bacteria, we do not require the reactive oxygen species. And in this case, the lactoferrin will bind to the iron, so that the iron does not undergo the Fenton reaction, producing ROS. We don't want ROS in that case if there is no pathogen. So this is the function of lactoferrin. Basically, in the summary, it is an iron binding protein in neutrophils that deplete iron from bacteria and also prevent the Fenton reaction. This is the end of the lecture. This is the last slide. Does anyone have any questions, or should I move on? I have some practice questions for you guys. I got them from previous batches, previous finals. So if there's no questions, so I can go through them really fast. Let's go through the questions. So I will read. We have a researcher uses a cell line to understand the iron regulation. Okay, iron regulation. She develops a knockout cell line that cannot express duodenal cytochrome B on the apical surface. Which process of iron absorption is likely decreased in this cell line? Now remember the function of duodenal cytochrome B. What is the function of duodenal cytochrome B? Exactly, it's A. Because the duodenal cytochrome B, it converts the ferric iron to ferrous iron so that we can absorb it. Okay, because remember, our body can only absorb ferrous iron هو the Fe2+. Okay, and most of the iron in the food is in the ferric state, so we need something that converted. So this is the duodenal cytochrome B. This is the easy one. Actually, this is a previous question in the final. طيب, a 48-year-old woman with a rheumatoid arthritis, okay, presents with worsening fatigue and shortness of breath. Her present complaint is caused by an increase in a peptide hormone produced by the liver that regulates iron homeostasis. This hormone works in which of the following ways? Now, before, let me see. No, now, yeah, exactly. It's E. The answer is E. Why? What protein are they talking about? They are talking about hepcidin, right? Hepcidin. This is the peptide hormone produced by the liver. So how does it occur? What like stimulates iron release? No, it inhibits iron release. We said that when we have a lot of iron, the hepcidin will be produced, and then it will do two things. It will inhibit the release of iron from macrophage, and it will inhibit the iron absorption from the enterocytes. Got it? Exactly, yeah, it's hepcidin. Okay, tamam. Now in the previous past, the past questions for the 14th patch, our patch, they had a mistake in which they did the answer for this as D. It's wrong, okay? It's E. Because in the file it's written as D, however it's wrong. It should be E. Okay. Now transport of iron from within intestinal enterocytes to the circulation requires that it should be oxidized from the ferrous to the ferric. This oxidation is catalyzed by which of the following proteins? Exactly, E. It's hepcidin. It's not B. B, the DMT1. Remember, this is the transporter of iron. It will transport the ferrous iron. Remember the DMT. It will you will have the Fe2+, and this ferrous iron. This is the lumen of the GI. Okay, the iron is here. This is the enterocyte. The DMT1, it will transport this iron inside the cell. However, it will not oxidize it from the ferrous to the ferric form. Now, if you remember the image, hepcidin is here, right? This is hepcidin. It will oxidize Fe2+ into Fe3+. Why? So that Fe3+ can bind to transferrin, right? Because transferrin can only bind Fe3+. Right. To hepcidin.
Can I ask you one question, please?
Yeah, sure. Go ahead.
Just to make sure. So, can you go back to question number 3?
Sure. Okay.
So from ferric to ferrous,
yes,
no. From duodenal cytoplasm B or like.
Yes. So let me go back.
From ferrous to ferric is hepcidin E. Right?
Exactly. So from the ferric, from Fe3+ to 2+ is by the duodenal cytochrome B. Okay, this is in the lumen of the GI, because we said that we can only absorb Fe2+. So we need something that convert 3+ into 2+, which is by the duodenal cytochrome B. However, in the other side here, if you remember the enterocyte, we have the hepcidin, which will convert Fe2+ into 3+. So it's the opposite exactly, because the transferrin can only bind 3+. Got it?
Yes, thank you.
Tamam. Delivery of iron to the cells by receptor mediated endocytosis requires which of the following? Albumin, cytochrome A1, ferredoxin, ferritin, or transferrin? Exactly, it's transferrin, because we said that transferrin is the transport protein for iron, and it is the one that will get iron from the plasma and then go into the cell by binding to the TFR1, the transferrin receptor 1. Yes, it's E. With that, I am done. Please, if you have any questions, you can message me or send me an email. Does anyone have any questions? Okay, thank you so much.